In this lecture, what I would like to talk about are what's called the Jefimko equations. Okay, so essentially what we're going to do is we're going to start with potentials in calculated from the retarded times. So we'll call them retarded potentials. V, R, and T, A. So we're measuring these at some position R and some position and some time T. And what we want to know is, what about calculating the electric field in this kind of very general case? So we're going to start with the, like I said, we're going to start with the potentials that we did in the previous lecture, where we start with essentially a Coulomb's law version of them, but they're time dependent. And the time of the charge and current is at some time in the past, and we're trying to measure the potentials now. So if we do that, we measure the potentials with the previous forms, which I might as well write out. So you do this enough times, you can kind of remember what the form of the potentials are. Okay, so this is our starting point. Now we want to calculate electric field. Okay, so we know we have a kind of a form of the potentials. The electric field, if you remember, we can calculate as minus the gradient of the electric potential minus the time derivative of the magnetic potential. So we're going to do this kind of from general principles. So what we're going to do is first take the gradient, which we've already seen before. And this was minus rho dot over C r hat over r minus rho r hat over r squared, integrating over the volume, like this. For the time-dependent derivative, we essentially have mu 0 over 4 pi and j dot. So we take the time derivative of the current. This distance is not changing in time. Integrate over the volume. So those are the two pieces. And the question is, can we really clean it up from here? So let's give it a try. So first I'm going to write everything out. 1 over 4 pi epsilon naught, taking the integral, and we're going to integrate, let's see, so it's minus the gradient, so the minus sign cancels. In the gradient of v, the minus sign cancels, so I get a positive rho r hat over r squared plus rho dot, so time derivative of rho, r hat over r, minus, so we get the minus sign from the definition of the electric field right here. So minus j dot, time derivative of j, c squared over r, and then we're going to integrate over all of that over the volume in the prime system. Okay, so remember that rho is a function of the position r prime and the earlier time. T sub r. So this is kind of like now a time-dependent version of Coulomb's law. So when we were talking about the statics case, in the statics case, what you had was 1 over 4 pi epsilon naught rho r hat over r squared integrating over the volume. Now we've got these two extra terms. We bring in the time dependence. We see how the charge distribution is changing with time, as well as how the current is changing with time. Okay, so now let's take a look at the magnetic fields. The magnetic field, we're going to calculate the curl of the potential A. So this curl of the potential A, we're going to get mu 0 over 4 pi, the integral 1 over r, the curl of J minus J cross product with the gradient of 1 over r, and then we integrate that whole thing over the volume. So that's right up in here. So I'll put that in there. So we're integrating over over the volume. So basically I had to take the chain rule with the cross product. Okay, so let's work out some of these pieces. So if I just look at the x component of the curl of the current, what I would have is the derivative of the z component of the current with respect to y minus the derivative of the y component with respect to z. Now djz with respect to y, I can write down as the time derivative of that component, and then the derivative of the retarded time with respect to y, which is another way of saying minus 1 over c, the time derivative of the current, the z component of the current, and then this is dr dy. Because remember, the our time now doesn't change, but the distance may be dependent on y. Okay, so if I put that all together, this one component of the curl of the current, so this one x component, would be minus 1 over c, the time derivative of the z component of the current, dr dy, minus the time derivative of the y component of the current, dr dz, which is essentially writing 1 over c, the time derivative of the current, the x component, no, I'm sorry, is writing the time derivative of the current crossed into the gradient of r, just the x component of that. So that's what we're going to get. When you take the curl of the current, you're actually going to get the time derivative of the current crossed into the gradient of the difference in position. And so now if we put in a couple of the other pieces, the gradient of r, we said, is r hat. The curl of the current is now 1 over c, the time derivative of the current crossed into the r direction. The gradient of 1 over r, we said before, was minus r hat over r squared. And so if we now put some of this stuff together, what we get is the magnetic field at some position r at some time right now t is mu 0 over 4 pi, the integral of the current at a position r prime at a time tr divided by r squared plus the time derivative of the current at those same position and times divided by c over r crossed into the r direction, and then you integrate over the volume. So again, what you get is a new time-dependent Biot-Savart law. So before, the static Biot-Savart law was that equation right there. And so now what we have is a second term, a time-dependent term, basically looking at how does the current change with respect to time. So we've got a static piece, so the magnetic field you get or the current just flowing through the wire, let's say, or over the surface or over the volume, but you also get a contribution to the magnetic field from changes in the current over time. And so now what we have is essentially updated equations, one of them being the new Biot-Savart law, and the other one being the updated Coulomb's law. So now we have much more general cases. We can consider now calculating the electric field and magnetic field when current and charge are static, when current and charge are changing. And we also considered, all of this from the start was the Lorentz gauge, where information cannot travel faster than the speed of light. So another aspect of this is that these equations hold for special relativity. Okay. Okay, so we'll stop here, and then in the next lecture, we'll go a little bit further and consider generalized cases of the retarded potentials.